After decades of importing telecoms equipment from the West, Russia has begun manufacturing its own mobile base stations. Aside private efforts by Irteya and Yadro, there are also state-controlled manufacturers like Bulat and NatsSpectr also vying for market share. After a period of rapid growth in the 2000s, Russia's economic expansion began to slow down during the 2010s. Under President Medvedev, the government attempted to replicate the American model of tech and venture capital by launching startup incubators like Skolkovo and creating the Rosnano Fund to invest in high-tech companies. But these efforts saw limited success. By the late 2010s, with Vladimir Putin back in office, Russian policymakers turned to a state-planned approach, directing major state-owned companies to develop strategic technologies deemed critical by the government. In July 2019, the Russian government signed a series of agreements with major state-owned companies to develop strategic high-tech areas. Rosatom was tasked with quantum computing, Russian Railways with quantum communication, and Sberbank with artificial intelligence. Rostec, together with Rostelecom, was entrusted with developing fifth-generation telecoms equipment. Bulat, the company initially tasked with the effort by Rostec and Rostelecom, began as a partnership between the two state-owned entities in 2016. However, the structure changed when Rostec decided to branch off and create its own venture, Spectra. Since then, Bulat has focused on making servers, switches, and routers tailored for data centers. Bulat is also a maintainer of Russia's underwater fiber optic cable lines. Bulat is the contractor of Rostelecom for the construction of underwater fiber optic cable lines in the Baltic, Arctic, and the Far East. Rostelecom chose its Bulat subsidiary to develop the unit because it was the most prepared to develop base stations. They already had some elements that make up base stations. Their routing product already contained a platform that could serve as a basis for a base station. The Bulat base station doesn't start as an internal project. To speed up development, Bulat outlined the specs for the base station, but the real development work took place at the Research Institute of Radio, NII Radio, a major state research center in Russia. NII Radio is the largest state research center for communications equipment in Russia. It conducts research into telecoms equipment, navigation equipment, satellite telecommunications, and secure communications. The center develops and manufactures smart antennas, onboard repeaters, and radio electronic facilities for various purposes. NII Radio have been busy since 2015 developing 4G base stations along with private telecoms equipment company Laboratory of Info Communications Networks, LABIX. LABIX makes micro base stations for enterprise, airports, subways, factories, and other private networks. The 4G LTE development was started in 2015. In 2021, the consortium also began developing 5G technology, but soon realized they needed to add 2G backward compatibility to win over Russian telecoms contracts. By 2022, they finished testing the 4G base station, but the new unit didn't meet all Bulat's requirements, so it was sent back for rework. The Bulat unit supports 2G GSM and 4G LTE operating in the 1800 MHz frequency range. The total solution includes a baseband unit, radio relay equipment, as well as antennas, a power supply system, and batteries, all from local suppliers. The software is provided by New Telecom Solutions LLC, a Russian telecom software company. Apart from NII Radio, Bulat also collaborates with the Ishvek radio plant and NPF Micron to source components. In 2023, Bulat and NII Radio completed initial field tests installing 20 base stations on Tele2's network. They landed contracts with major mobile operators, Tele2 and Megaphone. Bulat committed to providing 17,000 base stations to Tele2, another subsidiary of Rostelecom, and up to 5,000 for Megaphone by 2026. The Bulat base station is a carrier-class base station, best suited for less densely populated areas like small towns and villages, and will struggle in densely populated areas like in large cities. Settlements of up to 500,000 people can be supported by this device, but the unit cannot support cities with a population of over 1 million. Bulat is developing a macro base station to suit that need. This will provide a new hardware platform for the data processing unit, a new set of acceleration cards, and a transition to MIMO antennas. Bulat is also transferring foreign technology from its partnerships with Chinese equipment provider Irteya. The remote radio unit has 4 transmitters, each operating at 40 watts with speeds reaching up to 450 megabits per second and a radius of around 20 kilometers, supporting up to 900 active users per base station. This is comparable to Nokia and Ericsson's 18 MHz LTE systems that also support up to 900 users simultaneously with 3 sector base stations at around 300 users per cell. Production was outsourced to another Rostelecom subsidiary in 2024, a company called the Russian Telecommunication Technologies in St. Petersburg. By the end of 2025, Tele2 had installed more than 1,000 Bulat base stations. The Bulat base stations were initially installed in 10 small towns in the Nizhny Novgorod area, serving around 5,000 subscribers on Tele2's mobile network. In 2025, Rostelecom launched 8 Bulat base stations in the Krasnoyarsk territory in Siberia. There is no news yet on when their 5G equipment will be ready for introduction. Russian telecoms equipment makers face a situation similar to Chinese vendors in that they have lost straightforward access to Western semiconductor supply chains, but unlike Huawei or ZTE, they do not have large, mature domestic chip industry and component supply chains. Their supply strategies therefore involve a mix of limited indigenous development, use of Russian-designed processors, reliance on state-backed microelectronics firms, Chinese components, and grey market or indirect sourcing of Western components. The Russians are very weak when it comes to semiconductors. They have good design experience with fabless companies like MCST, which designs long instruction Elbrus chips, Baikal, which designs Baikal ARM and RISC-V chips, Syntacor and Cloudbear, which design RISC-V CPUs, but Russia has very little experience in designing FPGAs and ASICs, except for companies like Cloudbear and Malt System, but the density and performance lag far behind Western devices. So most of the current FPGAs in Russian equipment are most likely from the likes of Intel and AMD. With chips like the 48 cores Baikal BES1000 and the 32-core Elbrus 32C, the Russians can design somewhat competitive CPUs with large numbers of core counts, but they have big problems with fabrication at profitable volumes. Due to such limitations, the majority of CPUs in their equipment are most likely from American giants Intel and AMD. A big limitation is that they don't have the fabs to make high-end chips. Most of their designs have to be fabricated abroad in China after Taiwan's TSMC stopped fabricating chips on their behalf. Russian fab Milandra can fabricate up to 28nm chips, but in small quantities. Their biggest fab, Micron, can only fabricate about 90nm at high volume, but current high-performance chips require sub-10nm process nodes for high performance and power savings. The reality is that their products are not competitive in a performance-driven commercial context. The less efficient process nodes and older architectures mean more energy is consumed per bit of data processed, increasing operational expense significantly. So until their chips get closer to the performance of global giants, most of the CPUs in Russian base stations will most likely be from Intel or AMD. The Russians also have a problem when it comes to hardware accelerators. Radio units and distributed units require FPGAs or ASIC chips, but the Russians are very weak in the semiconductor category. STC Module is a Russian company that makes accelerators. They make the NM Quad module, a special accelerator based on 4 multi-core DSP processors in a PCIe card form factor. But its architecture makes it poorly suited for the high-throughput, low-latency signal processing tasks required in modern 5G base stations. Another Russian accelerator company is High-Tech LLC. The High-Tech company makes the Link-Q TPU accelerator. This TPU is an excellent component for accelerating the AI and machine learning workloads. But this card is also not designed for telecoms acceleration. So Russian gear vendors will most likely buy purpose-built Western accelerators or get Chinese ones. Russian-designed converter ICs from key developers like Design Center Soyuz, Physica, ZNTC, and Micron fall significantly short of performance requirements for modern 5G infrastructure. The core limitation lies in insufficient speed, specifically in 2 critical areas: sampling rates and interface throughput. Chipmaker Milandra seemed to have the only converter ICs feasible for base stations in Russia. Milandra's 40nm analog to digital converter chip can be used for 5G gear where the highest possible data rates and modulation schemes are not required. For many 5G applications, especially small cells or systems using 256 QAM, an ADC with this level of performance is entirely adequate. But for the most demanding macro cell applications, it is not. In telecoms networks, frequency dictates the choice of power amplifier. While LDMOS transistors are great for lower frequency bands like 2G, 3G, and 4G frequency bands, they struggle with higher 5G frequencies, from 3.5 GHz and above. For these 5G bands, gallium nitride is the preferred technology. Gallium nitride offers superior power density, higher breakdown voltage, and better thermal conductivity than LDMOS, enabling more powerful and efficient amplifiers in a smaller form factor. However, GaN comes with its trade-offs. It's more expensive and presents manufacturing challenges, particularly in achieving the linearity needed to amplify signals without distortion. Due to its performance advantages, GaN has become the cornerstone for 5G infrastructure, fueling a competitive market with key players like Cree, Wolfspeed, Quovo, NXP, and Sumitomo. In Russia, the Elements Group, parent company of Russia's biggest chip fabs, has a Siberian fab subsidiary called the Research Institute of Electronic Technology, NIIET, which fabricates both LDMOS and GaN transistors. Russia has developed an ecosystem of specialized companies producing radio frequency amplifiers for 5G and other advanced electronic systems. These entities form a collaborative chain from fundamental components production to full system integration. The key players include Ishtok State Scientific Production, a player in microwave electronics with closed technological cycles for development and production. Sosvedie, who acts as a systems integrator, developing advanced amplifiers in collaboration with VSU Design Center, which utilizes gallium nitride transistors manufactured by NIIT. Micron and Pulsar, who function as specialized manufacturers, with Micron focusing on low noise and power amplifiers for telecommunications and radar, and Pulsar specializing in assembling the chips for RF amplifiers and power electronics. And finally, Microwave Systems, who also make GaN pulse amplifiers for transport layer telecommunications networks. The Element Group also collaborates with MIPT Telecom to develop radio signal amplifier modules and power supplies for base stations to be supplied to the likes of Irteya. Russian chip company Milandra also develops GaN S-band power amplifiers operating in the 2 to 4 GHz frequency range for 5G mid-band deployments. Volumetric resonator filters are fundamental components for clean signal receiving and transmission in radio units. The operation relies on three-dimensional metal or dielectric cavities tuned to specific shapes and sizes to resonate at target frequencies. This enables them to effectively suppress unwanted signals and interference, leaving behind clear signals. Multiple filters, each handling a distinct frequency band, work together within a radio unit to enable precise frequency selection. Volumetric resonator filters are primarily deployed in high-power, stability-critical applications within the sub-6 GHz macro base stations, where their superior power handling, ultra-low insertion loss, and exceptional temperature stability justify their larger size and costs. These characteristics make them indispensable in 2G, 3G, 4G, and 5G macro cells, particularly for high selectivity filtering in congested urban environments where signal integrity outweighs space constraints. In contrast, surface acoustic wave filters dominate cost-sensitive low to moderate power scenarios below 3 GHz frequencies, leveraging compact size and affordability but suffering from thermal drift and insertion loss at above 2.5 GHz. Bulk acoustic wave filters outperform surface acoustic wave filters in 5G due to the ability to handle higher frequencies, greater power, and harsher environmental conditions. while surface acoustic wave filters struggle above 2.5 GHz due to energy loss and signal degradation, bulk acoustic wave filters operate efficiently from 2.2 GHz to up to 7.5 GHz, making them ideal for 5G mid-band and millimeter wave deployments. In Russia, the Technopark company makes surface acoustic wave, bulk acoustic wave, and dielectric ceramic filters under the Saw Techno brand. But their product line is not extensive, so they also import some filters from China and Taiwan. Most Russian gear vendors design and manufacture volumetric resonator filters in-house. Key suppliers include Micron, offering volumetric, dielectric, and waveguide filters, MIPT Telecom, which integrates its filters into transceivers and is expanding its off-the-shelf lineup, as well as Radiocomp and Matrix Wave, which also produce filters for radio unit equipment. The Russian ecosystem for network interface cards is not well developed. While domestic companies like Graviton, Digma, and Integral produce network cards, these are largely suited for enterprise or general-purpose computing environments. Models like Digma DPE101G or Integral's TrustNet cards are fundamentally not designed for the extreme throughput, low latency, and specialized features required in telecoms network infrastructure. Some domestic efforts like the Megapolis Telecom's HomeNet have attempted to address the commercial-grade market by introducing network cards like the 10 gigabit HNX 540 and HNX 520. However, these solutions are not proprietary, but are themselves built directly around Intel's X540 and X520 chips. Milandra produces Ethernet controller chips, but its offerings are fundamentally outclassed, lacking the port speeds of 10G, 25G, 100G, and 400G that are the baseline for 5G front-haul, mid-haul, and backhaul connections. Russian company Research Center for Electronic Computing, NICEVT, has developed the Angara 2, a high-speed interconnect card for data centers. The system, it's built around a proprietary network chip manufactured on a 65nm process and is architecturally optimized for high-performance computing workloads. A logical strategic move would be to leverage this expertise to develop competitive Ethernet network cards tailored for the demanding 5G gear market, like how their Western competitors successively offer both fabric and Ethernet products. Craftway, another Russian computer maker, has also begun making high-performance network cards for data centers using their own chips. Consequently, Russian domestic gear industry, yet to develop 5G network cards, will most likely use foreign cards from the likes of Intel and Broadcom. Russian defense contractor conglomerate Rostec has also been in the process of developing a Russian base station for a while. It established a telecoms equipment subsidiary called Spectra or Spectrum in 2021 to make 4G, 5G base stations even before Western sanctions and the withdrawal of global telecom giants Ericsson and Nokia from Russia. Spectra collaborated with another Rostec subsidiary, the Sosvedia company, a cornerstone of Russian communications equipment, often compared to Motorola due to its production of comms equipment for emergency services, law enforcement, and military. The technical development involved a consortium that included MPK Kryptonite and the State Research Radio Institute NII Radio. By 2020, a functional 5G base station prototype was demonstrated at the Conference for Digitalization of Industrial Russia. The R45F base station developed under Rostec was an Open RAN compliant system and consisted of 3 core parts: a 5G core, a digital processing module, and a radio transmitting module. The equipment was initially designed to operate in the 3.4 to 3.6 GHz band, which is the preferred frequency band for 5G globally, though in Russia this frequency band is unavailable because it's used by the security services. In 2022, Rostec pivoted from developing the 5G equipment to focus exclusively on 4G LTE, a shift driven by limitations in Russia's domestic supply of advanced electronic components. However, by late 2023, Spectre encountered significant financial and market difficulties. Telecom operators were hesitant to adopt untested equipment from a new player when established options from Huawei and Nokia were still available. This lack of commercial uptake prevented the extensive real-world testing needed to refine the technology, leading to frozen projects, staff reductions, and a cash shortage. In a strategic move to salvage the initiative, Rostec merged Spectrum with the NatsProm Group in 2024 to form NatsSpectr. This restructuring provided a necessary cash injection, with NatsProm supplying funding and Spectra contributing to the technology. This new entity began delivering its first 4G base stations later that year. Production is being carried out in collaboration with Elements Group at its Tom's Semiconductor Devices plant. Like Huawei, NatsSpectr appears to have developed its own acceleration chips. In 2018, the Russian chip design company Cloudbear designed a RISC-V-based hybrid accelerator chipset for base stations. The chipset is a scalable high-performance system-on-chip processor designed for physical layer computing and consolidating computations from multiple base stations. Cloudbear, founded in 2015, is Russia's #1 RISC-V chip designer, ahead of Syntacor. In 2016, it started developing the Cloudbear baseband processor IP and accelerator core. This chip contains a mix of DSP cores, RISC-V scalar processors, and hardware accelerators to handle computationally intensive tasks like MIMO processing, encoding, decoding, and forward error correction. The chipset employed a hybrid ASIC approach to balance flexibility of FPGAs and efficiency of baked-in cores. However, it seems this chipset did not make production. FPGAs dominate the prototyping phase and early years of a new generation base station, allowing rapid iteration without high costs. But once the standards are settled, most designs transition to ASICs for volume production, reducing power consumption and cost per unit. This hybrid ASIC approach ensures that reconfigurable interfaces and experimental features remain FPGA-driven, while performance-critical physical layer processing is handled in baked-in ASIC cores. The chip architecture aligns with the modern base station setup, where base stations require both adaptable interfaces of FPGAs and computational brute force of ASICs to support massive MIMO beamforming and ultra-reliable low-latency communication. Due to its military connections, Rostec has influence on most of Russia's electronics industry. It has controlling stakes in chip manufacturers Micron and Milandra, who make power systems, amplifiers, digital-to-analog converters, and transceivers. It also has subsidiaries like Sosvedie, who make radio communications products. For development of 5G components, they collaborated with research institutes including the Research Institute of Electronic Technology (NIIET) and the Research Institute of Molecular Electronics (NIIME) to develop and produce the necessary radio modules and other components. Rostec is also working with the Izhvek radio plant and the Micron company on other base stations. Micron and Izhvek radio plants make massive MIMO antennas, transceivers, filters, and other telecoms components. NatsSpectr launched its first production samples in 2024 and started mass producing in 2025 at the Arizan radio plant. The company intends to roll out 5G services in 2 unnamed cities by 2026, with aspirations to expand to 16 cities by 2030. The NatsSpectr line now also includes base stations that work in the 800, 1800, and 2600 MHz bands. Other Russian firms are also joining the telecoms gear market. Companies like NTT, Trailink, Rytech, Tenet, Telcor, Softim, and Protai are focusing on micro base stations for places like factories, airports, and campuses. And while these smaller players might find it hard becoming major suppliers, they could still find opportunities if Open RAN standards gain traction in Russia. China has decisively won the 5G gear race through state-driven scale and technological sovereignty, deploying 4.4 million base stations covering 76% of its population and dominating 70% of the global infrastructure revenue. Huawei and CTE achieved this with subsidized R&D, free spectrum allocation, and breakthroughs like domestic GaN power amplifiers and 7nm chips circumventing US sanctions. Europe secured second place through regulatory cohesion, trusting equipment, and vendor lock-in, helping Ericsson and Nokia keep market share. The US facilitated Europe's position by prioritizing China containment, convincing allies to stop using Huawei gear and preventing American chip companies from providing them high-tech semiconductors. This policy also helped South Korean and Japanese gear providers like Samsung and NEC. India emerged third as a disruptive latecomer, leveraging Tejas and Jio's affordable equipment to help build 470,000 stations in 3 years, though they have yet to gain market share internationally. Russia trails distantly behind, only now beginning to join the club. Their efforts were crippled by sanctions and the lack of modern chip fabrication. Paradoxically, the sanctions also stimulated the domestic industry, as local telecoms operators were forced to allow local manufacturers the chance to mass test their equipment on their networks, providing manufacturers with vital real-world experience needed to improve their products, thus accelerating product maturity. They were also helped by the proliferation of Open RAN standards and access to Chinese component imports, but the sanctions delayed any meaningful 5G rollout until 2030, when rivals will be preparing to pivot to 6G. The Russians have started research into 6G and are developing 6G systems, but if they are only completing 5G installations by 2030, the operators will be reluctant to upgrade their systems to 6G after they just spent money upgrading to 5G. This means Russia will likely be late for 6G also, or most likely 6G will only be installed in the big cities where demand is great, but the rest of the country will stay on 4G and 5G till the 2040s. Well, that's it, folks. Please like, subscribe, and stay tuned.